Okay, so let's dive in. We're looking at something, well, frankly, bizarre today. Just a little teardrop of glass.
Right.
But the sources you sent suggest this is way more than just glass. It's called a Prince Rupert's drop.
Exactly. And it's presented less as a curiosity and more as a key to understanding some pretty fundamental stuff about structure, motion, maybe even time itself.
And the core of it is this amazing paradox, isn't it? You
Yeah.
can, like, hit the fat end, the bulb, with a hammer, and it just shrugs it off.
Yeah, it's incredibly tough there, but then you just snap the tiny, thin tail.
And boom, the whole thing just disintegrates
It-
instantly into powder.
It completely messes with your intuition about how things break. Strength and weakness seem totally reversed.
Right. And the material we're looking at argues this isn't just weird. It actually, quote, breaks reality, or at least our standard assumptions. So our mission for this deep dive is to figure out why. Why does it do that? We'll explore two main viewpoints from the source, the traditional one, which it calls legacy science, and then this other perspective, this motion theory.
Yeah, and that's where it gets really interesting. The source suggests the real secret isn't just about stress, though that's part of it, obviously. It's about something deeper, like motion hanging on by a thread.
Motion hanging by a thread.
Yeah, ideas like synchronization, rhythm, right down at the atomic level.
Okay, wow. So let's start at the beginning, like the source does. How do you even make one of these things? It sounds simple. Drip molten glass into cold water.
Sounds simple, yes. But that rapid cooling, that's where all the weirdness gets locked in. The outside layer of the glass hits the cold water and hardens almost instantly.
Right, like a super fast quench.
Exactly. But the inside, it's still molten, still hot. And as it cools down much more slowly, it tries to shrink, to contract inwards.
Ah, but the outside is already solid, like a shell. It can't give way.
Precisely. So the inside is pulling inwards, but the outside is holding rigid. This sets up these incredible internal forces.
Massive forces. The source says the outside ends up under extreme compression.
Which makes it incredibly strong, yeah.
While the inside is stretched, basically, it's under severe tension, inherently unstable.
It's like this internal battle frozen in glass, compression pushing in on the surface, tension pulling out from the core, a state of extreme stored energy.
Okay, so that brings us to the first explanation, what the source labels legacy science. This view says it's all about releasing that stored stress, right?
Yes, that's the standard physics explanation. You've got the compressive strength on the bulb, making it tough. But the tail is part of that tense interior structure.
So breaking the tail is like pulling the pin on a grenade. It releases that internal tension.
Kind of, yeah. Legacy science describes it as initiating a catastrophic fracture wave. The release point, the break in the tail, allows cracks to just race through that highly stressed core.
And these aren't slow cracks. The source mentions speeds like, what, over 6,000 meters per second?
Insanely fast. Basically the speed of sound in the material, or even faster under these conditions. It just tears the whole structure apart from the inside out.
Okay, and the source acknowledges, look, this description is accurate. It does happen like that on the macro level.
Right. It says that explanation is correct as far as it goes, but it kind of stops at the surface.
Yeah.
It tells you what happens visually, but not the fundamental why behind the instant total disintegration.
Okay, so this is the jumping off point, where the source introduces motion theory. It says we need to look deeper than just stress. It talks about frozen motion under compression. What does that mean?
Well, that's the shift. Motion theory, according to the source, isn't just looking at forces, it's looking at what the atoms themselves are doing. That super fast cooling doesn't just create stress fields, it locks the atoms' movements, their vibrations, their interactions.
They're tiny dances, like you said before.
Exactly. The source calls them atomic motion loops, and these loops get frozen into a very specific, highly constrained, highly synchronized pattern, especially near the surface.
Synchronized. Okay. So the atoms aren't just stuck. Their movements are locked in step with each other because of the rapid cooling and pressure.
That's the idea presented. Near the surface, they're highly compressed and synchronized. Deeper inside, though, where the cooling was slower and the tension exists, the loops are described as less stable, kind of unresolved, straining against that outward pull.
So the whole drop is this delicate balance. The source calls it a rhythmic compromise.
That's a great phrase for it, yeah. A compromise between the tightly synchronized outer layers and the strained inner ones.
Wow. So the drop strength isn't just boot resistance. It's this incredibly ordered, synchronized motion. It holds together almost like like a formation dance routine, not a solid block.
That seems to be the core concept in the motion theory view presented here. Stability comes from this high degree of synchronization in the atomic motion loops. It's a dynamic stability.
Okay, but if stability is synchronized motion, then fragility must be.
Losing that synchronization. Break the rhythm, the source says. And the tail being the bottleneck where that internal tension is most concentrated or accessible, snapping it is like tripping the lead dancer.
And the whole formation collapses.
Instantly. Because those synchronized loops lose their coordination, their pathway.
Okay, and this connects to something else the source emphasizes. This idea that there's no time for recovery when the tail snaps. Which sounds weird, right? Time usually just flows.
Right, but here motion theory seems to frame time differently. Not just as seconds on a clock, but more like a measure of the system's ability to adapt. How fast can motion change or find a new stable pattern?
Ah, okay. So no time means no opportunity for the motion to reorganize. There's no available pathway for those atomic loops to shift into a different stable configuration once the original synchronized path is broken.
That seems to be it. The structure is so tightly wound, so rigidly synchronized, that its internal feedback or adaptability at that atomic level is essentially nil. Break the established pathway.
And there's nowhere else for the motion to go. It can't adjust.
Yeah. The source uses a really helpful analogy here. Think of a huge stadium doing the wave. Perfectly coordinated.
Okay, yeah, I can picture that rolling around the stands. That's the stable drop.
That's the stable drop, yeah. All the atomic fans moving in perfect sync. Now imagine someone near the crucial starting point suddenly messes up, stops, or goes the wrong way.
Right, it would disrupt the wave nearby. Maybe it fizzles out or gets messy for a bit.
In a normal stadium, yes.
Yeah.
But the source argues in the Prince Rupert's drop, because those internal atomic loops are under what it calls maximum sync pressure, they're wound incredibly tight. That initial break in sync at the tail doesn't just cause a stumble, it creates an immediate motion vacuum.
Whoa, hang on. A motion vacuum, not like empty space, but a vacuum of the required movement, the absence of the necessary synchronized pattern.
That's the concept, yeah. It really flips how you think about failure. It's not just stress exceeding strength, it's the absence of the required coherent motion needed for stability.
Okay, so this motion vacuum is fundamentally unstable.
According to the source, yes. It's an unsustainable asymmetry. The system needs that synchronized motion to exist, with no pathway for recovery, no time to adapt, and under that immense internal sync pressure, the internal loops just collapse, utterly.
And that's the disintegration. When those fundamental synchronized loops collapse, the source says you don't get a crack spreading, you get instant unraveling.
Exactly. The structure itself, which is structured motion according to this theory, simply ceases to be structured. It unravels.
It's less like breaking something and more like the motion just losing its form, its coherence.
Which is why the source calls the drop a perfect experiment. It shows what happens when structured motion loses its structure, total instantaneous failure.
Okay, let's try and summarize the two views from the source material then. We have the traditional legacy science.
Right, focusing on the macroscopic picture. Stored mechanical stress, compression versus tension, and a very fast fracture wave released when the tail breaks.
And then we have this motion theory perspective,
which digs down to the atomic level. It talks about the collapse of highly synchronized atomic motion loops. This collapse is triggered by breaking the rhythm at the tail, creating that motion vacuum.
leading to instant unraveling, not just cracking.
Exactly, a fundamentally different way of looking at why it fails so spectacularly.
And the really key takeaway from the motion theory angle, as presented in the source, seems to be this. The failure isn't about running out of time in the normal sense. It's about running out of rhythm.
Yeah, and running out of pathways for that motion to recover or redistribute itself. The structure is too rigidly synchronized to adapt.
It really paints the drop as this stark example of stability being highly ordered motion, and its catastrophic failure being the complete loss of that order, that instantaneous unraveling.
A demonstration of motion losing its form.
Which, leaves us with a pretty profound final thought drawing straight from this material. If stability isn't stillness, but this kind of high-level synchronization, and fragility isn't just weakness, but maybe a lack of feedback, an inability for that synchronized motion to adapt,
Right.
then what does that suggest about other things? Things around us that seem solid, stable, permanent? Are they truly static? Or, as the source provocatively puts it, are they maybe just motion loops pretending to hold forever?
It definitely makes you look at seemingly solid objects in a new light, doesn't it? What's really going on underneath that appearance of stillness?
A lot to think about there. Really fascinating stuff.